Now that we've had a chance to understand what exponential functions are, we are going to be looking at some ways that we can use exponential functions in different kinds of problems. So we're in particular going to be looking at some applications. First, we're going to briefly review exponential functions, just some of the things that we learned in the last video. We're going to do an application problem, and then we'll have a little discussion about the relationship between the base of our exponent and the rate of growth or decay. We've already had that discussion in one direction. If we know the rate of growth or decay, we can figure out what the base of our exponent is. Now we're going to do it in the other direction. All right, so remember that we have two ways of understanding an exponential function. The kind of conceptual way that we understand it is for each unit of change that we have in the inputs, the percent change of the outputs is the same. So for instance, if you go from 4 to 5, you may get a 5% change. You'll get a 5% change from 8 to 9 as well. It's just that it may be a different actual change, but the percent change is the same. And another way of looking at an exponential function is that it has the formula f of x equals a times b to the x. And here a and b are constants. A can be any constant, but b has to be positive and it cannot equal 1. So suppose you know that your function is exponential. The question we want to ask here is, how much information do you need to actually determine its formula? Well, if we look at the actual formula, f of x equals a times b to the x, to determine the formula, we really just have to figure out what a and b are. So what we really want to do is have enough equations so that we can solve for a and b. Since a and b are two unknowns, that means we need two equations, which we get from 2 points on the graph. So here's an example. So suppose you have an exponential function f, and suppose you know two other things about it. We know that f of 1 equals 20, so x equals 1, y equals 20 on the graph, and that f of 4 equals 30, so x equals 4 and y equals 30 is another point on the graph. So that's 2 points on the graph. We should be able to figure out the entire function just from that information. So the question we might ask is, well, what is f of 10? But to figure out f of 10, we actually have to figure out a formula for all values of x. So let's go ahead and do that. So we know f is an exponential function. That means that it has the formula f of x equals a times b to the x. A and b are constants. So we know what happens to the function at x equals 1 and x equals 4. Let's see what happens when we plug those in. So when we plug in x equals 1, we get f of 1, which is, by our given information, f of 1 is equal to 20. But we can also plug x equals 1 into our formula, a times b to the x. So we get a times b to the 1 is also f of 1, which means it has to equal 20. If we play the same game with x equals 4, we get f of 4 equals 30, which is given in the problem. And if we plug that into the formula, we get a times b to the 4, which then has to be equal to 30. So now we have two equations and two unknowns. We can use all those techniques from systems of equations from algebra that we've learned before. So probably the easiest thing to do in this one, there are lots of different approaches, but probably the easiest way in my eyes is to solve for a in both equations, right? So if we take the first equation and solve for a, we divide both sides by b to get a equals 20 over b. If we solve for a in the second equation, we divide both sides by b to the fourth. We get a equals 30 over b to the fourth. Now 20 over b and 30 over b to the fourth are both equal to a. That means they have to be equal to each other. And if we do maybe some cross multiplying and some simplifications, that gives us b cubed equals 1.5. If you have trouble with the algebra on that one, let me know. I'll help you through that. Now to solve for b, we're going to take the cube root of both sides. If we take the cube root of the left side, we get b. The cube root of the right side, we get a cube root of 1.5. So we're halfway there. We got our b. So actually, we're almost all the way there, because remember from our first equation, we got a equals 20 over b. We just figured out what b was. That's cube root of 1.5. That means a equals 20 over the cube root of 1.5. We know what a is now. We know what b is now. That means we know the function. There's our a, 20 over cube root of 1.5, times b to the x. Our b is cube root of 1.5. And if we wanted to figure out what f of 10 was, now all we have to do is just plug in x equals 10 into our equation. We get a times b to the 10. And then we pop that into our calculator. That's about 67.5. Same type of thing happens when we do exponential decay. So what happens when our exponential functions decrease? So in this case, we have f of 0 equals 8 and f of 3 equals 4. Notice that f of 0, even though that's the smaller input, it has the higher output than x equals 3. So a little bit different than the last problem. But we can still get a nice formula for the exponential function. So again, we know f is exponential, so it has the formula a times b to the x. F of 0 equals 8. We plug in x equals 0 into our function f of x. We get a times b to the 0. So a times b to the 0 equals 8. B to the 0 is just equal to 1. Anything to the 0 is 1. So that gives us a equals 8. Play the same game with, so now we have f of x equals 8 times b to the x, since we know what a is. Now we play the same game with x equals 3. We get f of 3 equals 4. Plug in x equals 3 into the function. That gives us 8 times b cubed is equal to 4. And then we solve for b the way we had before. B cubed equals 0.5. Take the cube root of both sides. We get b equals the cube root of 0.5. And that gives us f of x equals 8 times the cube root of 0.5 to the x. And if we wanted to find out what f of x was for a certain value of x, we just plug that in for x. So I want to have a little discussion about the two examples that we did. We did one with exponential growth, we did one with exponential decay, and I want to talk about when exponential growth happens and when exponential decay happens. So our first example, you remember, was f of x equals, we had our a, which was whatever, 20 over cube root of 1.5 times cube root of 1.5 to the x. I want to look at that b, that cube root of 1.5. This was an exponential growth problem. And if we look at that b, we get b equals the cube root of 1.5, which is about 1.1447. That shouldn't be a surprise to us. When we were doing exponential growth in our previous problems, we got numbers that were bigger than 1, and indeed, this one's bigger than 1. And indeed, the way we would find b when we did exponential growth is we'd take 1 and we'd add the rate of growth, add the percent rate of growth. So if we do that in reverse, what would we have to add to 1 to get 1.1447? That's going to be 0.1447, right? If we took that rate of growth, added it to 1, we get 1.447, which was our b, exactly like we did before. So now we're running that process in reverse, saying my b is 1.447. To get the rate of growth, I just subtract 1 from that. And so if you want to write that as percentage, that means every time we increase the x by 1, our f of x gets increased by 14.47%. We do the same thing with exponential decay. Remember our exponential decay problem, we had our b here was cube root of 0.5. And if we put that into a calculator, we get 0.7937. Again, not a surprise to us, that's less than 1, right? In our exponential decay examples, we got values of b that were less than 1. And in fact, if we wanted to find the rate of decay, what we would do was, well, if we knew the rate of decay, what we would do to get the b is we would subtract that rate of decay from 1. If we want to find the rate of decay knowing what b is, we would do the same thing. We would subtract that value from 1. That gives us 0.2063. And so our rate of decay is 20.63% for each unit that x is increased. So that just gives you a little bit of idea about how to take that process backwards, figuring out what the percent of increase or decrease is based upon what b is. And you'll get a few chances to work on problems like this. The name of the file is Exponential Applications, and it's included with this video.